right now, sitting, right there in the middle of your kitchen, there's this massive metal box performing a relentless, just invisible magic trick.
Yeah, a magic trick that honestly we all just completely take for granted.
We totally do. I mean, you walk up, you open the door, a little light turns on, you grab a cold carton of milk, and you close it, and it just feels like this magical machine that generates cold air out of thin air.
Right. Like it's just producing coldness.
Exactly. But the truth is, and this is what we're looking at today, a refrigerator doesn't actually create cold at all because, well, cold doesn't even exist.
It doesn't. And that is, it's a fundamental paradox of physics that trips a lot of people up,
You
actually.
trip me up for sure.
I mean, the concept of creating cold is a complete myth. In thermodynamics, cold isn't a physical thing you can just like produce or pump into a room. Cold is quite simply the absence of heat. So that appliance you trust with all your groceries is essentially performing a nonstop high-stakes extraction mission. It is like violently pulling heat out from the inside of that box and just dumping it right out into your kitchen.
And it's a trick that is constantly under attack by the environment around it, right?
Oh, absolutely.
So today, you and I are on a mission to completely demystify that box in your kitchen. We're going to decode exactly how it works, learn to translate the weird puddles and clicking noises it makes, and figure out the exact line between a 10-minute DIY fix and a complete multi-thousand-dollar disaster.
Which is super important for anyone listening, yeah.
Definitely. And to do this deep dive, we're looking at some fascinating diagnostic data gathered by appliance repair technicians down in Bradenton, Florida.
Which is just brilliant.
Yeah.
Because if you want to truly understand the extremes of refrigeration, and how these machines fail, you really have to look at an environment that actively fights against them.
Like Florida in the summer.
Exactly. The relentless summer heat and that thick, heavy coastal humidity in a place like Bradenton. I mean, it forces these machines to their absolute physical limits. It is the perfect stress test.
Yeah, that makes sense.
But before we can diagnose a broken machine, we really need to understand what it's trying to do when it's perfectly healthy.
Okay, let's unpack this, because if we look at the baseline refrigeration cycle, it really hinges on this delicate four-part relay race, right? You've got the compressor, the condenser, the expansion valve, and the evaporator.
Right. Those four components, they're the entire engine of this heat extraction magic trick. And the whole cycle, it always starts with the compressor.
Okay.
Think of the compressor taking a chemical refrigerant gas and literally squeezing it. It just constricts it down into a tight space, which dramatically raises the pressure and the temperature of that gas.
So I was trying to picture this mechanically, and if we look at the refrigerator as a living organism, the compressor is essentially the heart, right?
That's a great way to look at it.
Like, it's doing the heavy lifting, but instead of pumping blood, it is pumping this superheated high-pressure refrigerant through the system's veins.
Exactly.
And if you're trying to survive a Bradenton summer, this heart isn't just lightly jogging. It is essentially running a continuous high-speed marathon just to fight off the ambient temperature of your kitchen.
That is a highly accurate analogy, honestly.
Yeah.
So the compressor pushes that superheated gas into the next stage, which is the condenser coils.
Those are the ones on the back, right?
Right. Those metal grates you usually see hidden on the very back or sometimes underneath the unit. Their whole job is to radiate or basically release all that captured heat into the surrounding air of your kitchen.
Wow. Okay.
And as the heat escapes into your room, that pressurized gas cools down just enough to transform into a high-pressure liquid.
Okay, so it's a liquid now, but I still don't get how it actually gets cool enough to chill my groceries. Because so far, it just sounds hot and pressurized.
Well, this is where the magic happens. That liquid passes through something called an expansion valve. And this valve forces this highly pressurized liquid through a tiny, tiny opening into a much larger chamber.
Okay.
And when it hits that larger chamber, the pressure just drops instantly.
Kind of like an aerosol can.
Yes.
Like when you use a can of compressed air to clean your keyboard or you hold down the nozzle on a can of hairspray, the can actually gets freezing cold in your hand. Is that the same physics?
It is the exact same physics. It's called rapid expansion. When you drop the pressure of that liquid refrigerant so suddenly, it drops in temperature rapidly, becoming a freezing cold gas again.
That's incredible.
Yeah, and then that freezing gas moves into the final stage, the evaporator coils inside the actual furnace compartment. And there, it acts like a sponge, just absorbing the heat from your room temperature groceries, and then carrying that heat right back to the compressor to start the whole marathon over again.
And all of this furious pumping, squeezing, and pressure dropping is happening just to hit one magic number, right? 37 degrees Fahrenheit.
Yep, 37 degrees.
The data points out that 37 degrees is the absolute baseline required to keep bacteria from multiplying on your food.
Yes, and that brings us back to why that Florida factor is so critical to understand.
Okay.
Because when you have high ambient temperatures and, high humidity leaking into the kitchen,
Which it always is.
right, the compressor and the cooling fans, they have to work significantly harder. They run longer and longer cycles just to maintain that 37 degrees.
Yeah.
The whole system is incredibly delicate.
Yeah, I bet.
So when any single component in this interconnected cycle falters, the heat wins, and the internal temperature of the appliance inevitably rises.
Which perfectly transitions us into the main event here. Because of all this immense strain, eventually these parts are going to fail. And when they do, your fridge actually tries to talk to you. It gives you physical
It
symptoms.
does, yeah.
So let's play detective.
A few months ago, I had this exact scenario happen to me. I opened my freezer to grab some ice, and it was perfectly freezing. Everything was rock solid.
Okay, good so far. Right, but then I opened the main fresh food section, and it was totally warm. The milk was spoiling. The butter was melted. What is happening there?
Well, what's fascinating here is that your immediate thought, and honestly, almost everyone's immediate thought, is, oh no, the cooling system is broken. I need a new compressor.
That was exactly my thought. I panicked.
Right. But if the freezer is cold, the cooling system, that entire pressure and refrigerant cycle we just walked through is actually working perfectly.
Yeah.
The problem isn't the cooling. The problem is the circulation.
Wait, really? So the fridge doesn't cool itself?
Exactly.
Well,
Almost all the cold air for the entire appliance is generated in the freezer section, right at those evaporator coils.
oh, wow.
Yeah, there's a specific component called the evaporator fan motor,
Yeah.
whose entire job is to physically blow that freezing air out of the freezer through a vent and down into the fresh food compartment.
I had no idea.
So if your main fridge is warm but the freezer is cold, you don't have a broken fridge. You just have a stalled fan motor.
That makes so much sense. It's not the cold that failed, it's the delivery system.
Okay, but what about the opposite extreme? Say you open the freezer, and instead of just being normal cold, it looks like an Arctic tundra in there.
Oh, yeah.
Like there is a massive, heavy buildup of frost and solid ice all along the back wall, completely burying your frozen peas.
That symptom points directly to a failure in the automatic defrost system.
Hold on. Here's where it gets really interesting. Are you telling me a refrigerator actually has a heater built inside of it?
I am.
That sounds like the most inefficient engineering possible. Why put a heater inside a freezer?
I know. It sounds like a complete design flaw, but it's actually a brilliant mechanical necessity. Remember, the evaporator coils get incredibly cold to absorb heat.
Right.
But every time you open the freezer door, you let in room temperature, humid air. And in a place like Florida, that air is just soaking wet.
Oh, I see where this is going. Yeah. When that wet air hits the freezing coils, the moisture instantly turns into frost. And over time, that frost builds up into solid ice. So engineers equipped refrigerators with a defrost heater, a defrost timer, and a bimetal thermostat.
Okay, a bimetal thermostat, what does that actually do?
It's a beautifully simple mechanical trigger, honestly. It's literally two strips of different metals sandwiched together. And because they're different metals, they expand and contract at completely different rates when the temperature changes.
Oh, that's clever.
Right. So when the coils get too cold and frost starts building, one metal shrinks faster than the other, which causes the strip to physically bend.
Wow.
That bending motion clicks a switch, completing an electrical circuit that turns on the heater just long enough to melt the frost off the coils. But if any part of that trio fails, the heater, the timer, or that bending metal thermostat, the ice just keeps building.
But why is that ice such a bad thing? I mean, my instinct is that if a freezer is full of ice, it's just going to keep my food extra cold.
It feels like it should, right?
Yeah.
But in this specific context, solid ice actually acts as a thermal insulator. Think of it like putting a winter coat over the coils.
Oh, I see.
When those evaporator coils are encased in a thick block of ice, the fan can't blow air across the bare, freezing metal. The ice literally traps the cold against the coils and prevents it from interacting with the passing air.
That is wild.
Yeah, so ironically, having a massive block of ice in your freezer will eventually cause your refrigerator to stop cooling your food.
The ice insulates against the cold. That's wow. Okay, so speaking of melting ice, I have to ask about this next symptom because I've lived it. You walk into the kitchen in your socks and squish.
Worse.
You step in a massive puddle of water, you open the fridge, and water is pooling underneath the bottom crisper drawers, just overflowing onto the floor. where is that water even coming from if the inside of the fridge is cold?
Well, we just talked about that defrost heater melting the frost, right?
Yeah.
Well, that melted water has to go somewhere. During a healthy, normal defrost cycle, the ice melts off the coils, drips down into a small internal trough, and travels down a hidden drain tube into a pan underneath the entire refrigerator.
Underneath it.
Yeah, and down there, the ambient heat from the compressor just naturally evaporates the water back into the room.
So it basically has its own internal plumbing system.
Exactly.
Uh,
But if a tiny piece of debris, or even like a solid chunk of ice, clogs that internal drain tube, the water has nowhere to go. The heater melts the frost, the water backs up, overflows the trough, and spills right down the back wall of your fridge.
And pools directly under those crisper drawers.
Bingo.
So the fridge is literally overflowing its own gutters. Okay, let's talk about the noises. Kitchens have a lot of ambient hums, but sometimes the fridge gets loud. Symptom number 4. You're sitting in the kitchen and you keep hearing this distinct, sharp clicking sound coming from the back of the fridge. Click. Pause for a few minutes. Click.
Yeah, that's never a good sound.
My instinct, if an appliance is clicking, is just to unplug it, wait 10 seconds, and plug it back in, like a router. Does that actually do anything here?
Unfortunately, no. A reboot won't fix this, because that clicking is almost always a mechanical failure of the start relay.
What's a start relay?
It's a small electrical device attached to the compressor. Think of it like the starter motor in your car. When you turn the key, the starter gives the main engine the massive jolt of energy it needs to turn over.
Okay, yeah.
The start relay does the exact same thing for the compressor. So when it starts to fail, it tries to shoot that jolt of electricity to engage the compressor, fails, clicks off, and then tries again a few minutes later when it cools down.
Oh, man.
It's basically the sound of the engine desperately trying to turn over, but never actually catching.
Wow. Which brings us to the other noise, symptom number 5. Loud, aggressive humming or buzzing noises. And looking at the data from the Bradenton technicians, there's a very specific trick you can use to diagnose exactly where a hum is coming from.
Right, because not all hums are created equal. If you hear a loud humming, the very first thing you should do is simply walk over and open the freezer door.
Just open it.
Yeah. If the noise instantly stops the exact second you pull the door open, the problem is your evaporator fan.
Wait, why does opening the door stop the fan?
Because there is a small switch on the door frame that automatically shuts off the fan when you open it. So it doesn't blow freezing air right into your face.
Oh, that makes sense.
So if the noise stops when the fan stops, it means ice is built up inside the vent, and those plastic fan blades are literally smacking into a wall of ice at high speed.
Yikes. And what if you open the door, but that aggressive humming just keeps going?
The noise isn't inside the box. It's coming from the back of the unit, which means your condenser fan motor, the one sitting near the floor trying to blow the heat away from the compressor, is struggling.
And as we established with our Florida stress test, if that condenser fan dies...
Yeah, if it stops pushing the heat away, your compressor will overheat and fail.
Okay, so we've translated the language of the refrigerator. We know what it's crying out for. We know why it's leaking and why it's clicking. The natural next question for you, the listener, is, can I actually fix this myself?
Right.
We need to draw a very explicit line in the sand between vital preventative maintenance you absolutely should do and the dangerous territory where you need to back away slowly and call a professional.
And that dividing line is generally drawn between keeping the environment around the machine healthy versus opening up the actual pressurized mechanics of the machine itself.
Let's start with what we can do, the high DIY feasibility stuff.
Oh.
The technicians emphasize checking your door gaskets every 3 months. Now, we all know the gasket is that flexible rubber seal running along the outer edge of the door.
Yep.
And there is a ridiculously simple way to test it called the dollar bill test. You just close the refrigerator door on a standard dollar bill. If you can pull the bill out easily without any resistance, your seal is compromised.
And a compromised seal is an absolute nightmare for the lifespan of your appliance, especially in high humidity. If that seal degrades even a tiny bit, warm, wet room air is constantly leaking into the cold cabin.
It's essentially like leaving your home's front door wide open while your central AC is blasting on a 95-degree day. The machine just can't keep up.
Precisely. And it's not just wasting energy, it's actively destroying the machine. The internal temperature sensors detect the heat leaking in, so they tell the compressor to kick on.
And it just never stops.
Right, because the leak never stops, the compressor runs nonstop, running that high-speed marathon with zero breaks. You're essentially wearing out the most expensive, vital organ of your refrigerator just because of a $10 piece of failing rubber.
The other massive DIY maintenance task the experts stress is taking 10 minutes just twice a year to physically pull the fridge forward and brush or vacuum the condenser coils.
This cannot be overstated. Dust, dirt, and especially pet hair accumulate on those lower coils incredibly fast.
I can only imagine.
And remember the physics we talked about. Those condenser coils are exactly where the system releases the heat it stole from your groceries. When they are coated in a thick, insulating blanket of pet hair, that heat is trapped.
So it just bakes.
Exactly. It can't radiate into the room. The entire cooling cycle slows to a crawl, your energy bills spike, and your compressor will literally burn itself out trying to push heat through a fur coat. Vacuuming the coils is the single best preventative action you can take to delay mechanical failure.
Okay, so we can totally handle cleaning coils and checking rubber seals, but what about when things mechanically break? The data is very clear about when to call the experts, listing things like digital motherboards, delicate temperature sensors, and absolutely any time you are dealing with the chemical refrigerants.
This raises an important question, though. What is your personal threshold for risk? Because modern refrigerators are not just simple motors and belts anymore. They are highly complex, computerized ecosystems. Attempting a DIY repair on a sealed system, which is the compressor, the coils, and the pressurized refrigerant lines, is where you cross from maintenance into genuine hazard.
Yeah, the data explicitly mentions that doing a DIY on a sealed system can cause severe physical injury to you or cause permanent, irreversible damage to the unit.
Exactly. Professionals use specialized tools for a reason. They use multimeters to check electrical continuity, which is basically sending a small current through the wires to ensure the electrical bridge is perfectly intact and hasn't burned out.
Right.
They use heavy-duty pressure gauges to ensure the volatile chemical refrigerants are handled safely, and they use OEM, original equipment manufacturer parts.
So it's serious business.
Very. The physical safety risk of mishandling pressurized chemical gas is very real, but there is also a major financial risk here. You could easily turn a minor $100 fix into a total catastrophic system replacement just by poking around a sealed system and accidentally venting the refrigerant without the right tools.
Speaking of professional repairs, the data breaks down the timelines, which I find super helpful for just knowing what you're in for when you make the call.
Yeah, timelines are good to know.
If you have a standard repair, like replacing a bimetal thermostat, swapping out a stalled fan motor, or clearing a deeply clogged drain line, a pro is usually in and out of your kitchen in 1 to 2 hours.
That's right.
But if you have a sealed system failure, like a dead compressor, you are looking at up to 4 hours of heavy labor.
And it takes that long because it requires highly specialized recovery equipment. By law, they can't just vent the old chemical refrigerant into the atmosphere.
Oh, because of environmental regulations.
Yes. They have to use special vacuums and sealed tanks to safely capture the old gas, flush the lines, weld in the new compressor, and then perfectly weigh and inject the exact right amount of new refrigerant. It is a major surgical procedure.
And that massive time and labor calculation leads right into the ultimate replacement math, because a lot of people wonder if it's even worth fixing an older appliance when it breaks down.
It's the ultimate question.
Yeah. The data gives us a pretty clear formula for this. If your refrigerator is under 10 years old and the quoted price to repair it is less than 50% of the cost of buying a brand new comparable one, you should fix it.
But the math totally changes if it's an older unit. If your fridge is over 15 years old, you have to weigh the cost of a 4-hour compressor repair against the incredible compounding leaps in energy efficiency you'd get from a modern unit.
That's a good point.
Sometimes, keeping a 15-year-old fridge on life support costs you dramatically more on your monthly electric bill than you would spend just financing a brand new, highly efficient one.
So what does this all mean? We started today by zooming way in on the compressor and the coils hiding inside this one specific box in your kitchen. But the principles at play here actually push us to zoom out.
They really do.
Because the exact same physics keeping your milk cold and your food safe are the mechanical principles keeping your entire house livable.
If we connect this to the bigger picture, a refrigerator is simply a small, insulated box using a compressor and a chemical refrigerant to remove heat. If you look at your home's central air conditioning unit sitting outside your house, It is doing the exact same thing on a macro scale.
It's the exact same tech.
Yes, it is using a massive compressor and massive coils to steal heat from a larger box of your home and fight off that intense ambient weather. The mechanics are identical.
It's all incredibly connected. The technicians even point out how local environmental factors in your home affect multiple appliances all at once. Like if you have hard water quality issues or wildly inconsistent water temperatures, you might notice your kitchen dishwasher isn't cleaning plates properly and your laundry washing machine is struggling to clean clothes. But the actual root cause might not be those appliances at all. You might actually need a shower heater repair to fix the underlying plumbing and heating elements that service the whole house.
It is brilliant that you picked up on that connectivity. We have this tendency to view our appliances in total isolation.
Yeah, totally.
We think the fridge is just the fridge, the AC is just the AC, the dishwasher is on its own island. But they don't exist in a vacuum. They are part of a deeply interconnected mechanical ecosystem in your home, and they are all heavily influenced by the local environmental strain.
Which makes a ton of sense.
Understanding how the compressor in your kitchen actually works makes you a far more informed owner of your home's entire climate control and plumbing infrastructure.
All right, we have covered a massive amount of ground today. Let's recap the key actionable takeaways for you. Number one, go into your kitchen today and do the dollar bill test on your fridge door. If it pulls out easily, get a new rubber gasket before you burn out your compressor.
Very important.
Number two, take 10 minutes, pull that fridge away from the wall, and vacuum the pet hair off your condenser coils so the machine can actually breathe and release heat.
Yes, please do this.
And number three, if your fridge is making a loud humming noise, play detective. Open the freezer door. If the hum stops, it's your internal fan hitting ice. If it keeps humming, it's your condenser fan struggling, and you probably need to make a phone call to a pro.
Those are fantastic practical steps. But I want to leave you with one final thought to mull over, zooming back out to the physics of it all. We spend so much of our lives taking our modern conveniences for granted.
We really do.
But right now, all around you, you are surrounded by machines whose entire existence is devoted to a relentless, invisible war against thermodynamics. They are constantly stealing heat, moving air, and fighting the natural decay of entropy just to preserve your daily comfort and keep your food safe from the environment. Once you understand the sheer mechanical will required just to keep a simple box at 37 degrees, it really makes you wonder what other invisible, highly complex battles are being fought by the silent machinery hidden right under your roof.
It makes you look at your kitchen and your whole house in a completely new way. Well, that is our deep dive into the relentless heat-stealing magic trick of your refrigerator. Thank you so much for joining us, and keep seeking out those aha moments in the everyday world around you. We'll see you next time.